Hello students, welcome to my channel GVS Chem. In this video, I am going to explain abnormal molecular masses and Van 't Hoff factor. Please subscribe to my channel, like, share and comment my videos.
Abnormal molar masses. Now let us discuss the abnormal molar mass. For example, if potassium chloride is dissolved in water, it completely dissociates K plus and Cl minus. So here 1 mole, and here when it dissociates we get 1 mole of potassium ions and 1 mole of chloride ions. Totally there are 2 moles of ions. 2 moles of ions. We know that colligative property is nothing but colligative property depends on the number of solute particles, but not on the nature of the solute. So if we do not know the dissociation constant, we could be led to conclude the molar mass of 2 moles of ions. Potassium how much? 39. This is chloride 35.5. Therefore this is 74.5. We could be led to molar mass of 2 moles of ions be 74.5, and 1 mole of ions is how much? 37, half of this. So 1 mole of ions is half of this. Therefore this is 37.25. 37.25. So this is 37.25 is observed molar mass from colligative property, whereas actual molar mass is this. So when dissociation takes place, observed molar mass is less than actual molar mass. Observed molar mass, when dissociation takes place, observed molar mass is mass will be less than actual molar mass. Now let us consider the association. Ethanoic acid or acetic acid, 2 molecules of ethanoic acid associate with each other to form a dimer. This is known as a dimer. So association takes place in this manner. In between doubly bonded oxygen atom and the hydrogen atom of other molecule, a bond is formed, that is hydrogen bond. Because of the formation of a hydrogen bond, they associate with each other. So here number of particles decrease. As the number of particles decrease, colligative property also decreases. Therefore delta TB or delta TF becomes Hoff, whereas previously in case of potassium chloride which dissociate, delta TB or delta TF becomes double as the number of ions increases to double, whereas here number of associated particles decrease to half, 1/2 of it. Therefore delta TB or delta TF becomes half. So as colligative, if we calculate the molar mass, if we calculate the molar mass using this delta TB or delta TF, then calculated molar mass will be more, whereas previously the calculated molar mass is less. Therefore the calculated molar mass becomes more or less. More or less. So if a calculated molar mass becomes more or less, what happens? We do not get the correct molar mass of solute. So to rectify this, Van Hoff, a scientist, scientist Van Hoff introduced a correction factor. Correction factor. Factor I. Correction factor I. Who introduced? Van Hoff. So I equal to normal molar mass by abnormal molar mass. Normal molar mass by abnormal molar mass. This equal to observed colligative property by calculated colligative property. So this equal to observed colligative property by calculated colligative property. So here from this observed colligative property by calculated colligative property, which is equal to total number of moles of particles after association or dissociation by total number of moles of particles before association or dissociation. Here abnormal molar mass is calculated experimentally, whereas and calculated colligative property are obtained by assuming the non-volatile solute is neither associated nor dissociated. So if Van Hoff correction factor is included, delta TB, that is elevation and boiling point. What is the elevation and boiling point? Delta TB equal to KB into M. KB into M. If Van Hoff factor is included, this is I into KB into M. Similarly, regarding the depressional freezing point, delta TF equal to I into KF into M. Similarly, pi osmotic pressure I into CRT, where C equal to N by V RT. So this is osmotic pressure. Similarly, relative lowering of vapor pressure P0 minus P by P0 equal to N1 by N1 plus N2. N1 by N1 plus N2. This is equal to I into N1 by N1 plus N2. N1 is the number of moles of solute. N2 is the number of moles of solvent. Now let us see the degree of dissociation. Degree of dissociation is the fraction of total number of molecules which dissociate into simpler particles. For example, AB dissociates into A plus B minus. So here initial concentration is 1. Degree of dissociation alpha. So here alpha plus alpha. So let us consider a molecule dissociate into M particles, and degree of dissociation is alpha. Let us consider a molecule dissociate into M particles and degree of dissociation is alpha. Then number of particles after dissociation is, here how many left, as degree of dissociation is undissociated particles 1 minus alpha plus M alpha, dissociated particles M alpha. Then what is want to have factor? Want to have factor equal to number of particles after dissociation by number of particles before dissociation. Number of particles before dissociation. Therefore, I equal to number of particles after dissociation. How much is left? 1 minus alpha plus m alpha by 1. This is nothing but I equal to 1 minus alpha plus m alpha equal to 1 plus alpha you take as common factor m minus 1. So bring this 1 to this side. I minus 1 equal to alpha into m minus 1. So alpha equal to I minus 1 by m minus 1. So this is the degree of dissociation. Since I equal to mn by mo, that is normal molar mass by observed molar mass. Therefore let us substitute I in this formula. Alpha equal to I minus 1 by m minus 1 equal to I how much? Mn by mo minus 1 by m minus 1. This equal to mn minus mo by mo into 1 by m minus 1. Therefore, alpha equal to mn minus mo by m0 into m minus n. So what is mn? Mn is the normal molar mass, mo is observed molar mass, and m is the number of particles. So in this m we can replace by n in order to avoid the confusion. In dilute solutions, electrolytes like NaCl, CaCl2, what happens as the dilution increases, ionization increases. As ionization increases, number of particles increases. So as number of particles increases, as a result, I means Van der Hoff factor. I also increases. As a result, I also increases and reaches to maximum dissociation. Maximum dissociation means implies unity. That means 100%. Therefore, if a problem is given in this manner, I for NaCl dissociate into two ions, Na plus Cl minus. Therefore, Van der Hoff factor is 2. Van der Hoff factor for CaCl2 dissociates into Ca plus 2Cl, Ca2 plus 2Cl. Therefore, I equal to 3 here. Therefore, if no information is given and simply substance is given, then Van der Hoff factor is calculated by writing the number of particles released after dissociation. So this is dissociation. Now let us find the degree of dissociation during association. Association means solute particles associate. That we discussed already in the previous module. Ethanoic acid, that is acetic acid, two molecules of acetic acid associate to form dimer. So degree of association, alpha, is the fraction of total number of molecules that undergo association. suppose AB molecules associate to form ABM. So let the number of molecules, let the number of molecules or number of moles is 1. Alpha, degree of association be alpha. So here after association, number of molecules left equal to number of molecules left equal to 1 minus alpha. Now after association, number of molecules formed, equal to alpha by m. So total number of particles or molecules, after association equal to 1 minus alpha. This is the number of particles left after association plus number of particles formed by associating is plus alpha by m. Total number of particles before association is equal to 1. Now want Hoff factor equal to I equal to number of particles after association by number of particles before association. So this is, therefore I equal to number of particles after association is 1 minus alpha plus alpha by m, by number of particles before association is 1. So this is nothing but 1 minus alpha plus alpha by m. So 1 minus alpha plus alpha by m. Now bring this 1 to this side. I minus 1 equal to alpha by m minus alpha is equal to, if you take out as alpha as common factor, 1 by m minus 1. Therefore alpha equal to I minus 1 by 1 minus m, 1 by m minus m. Now what is alpha? What is I? I equal to m n by m o. Mn is normal molecular mass by mo is observed molecular mass. So let us substitute I in this formula. So if we substitute I in this, therefore alpha equal to mn by mo minus 1 by m minus 1. So this is, let us simplify this. So alpha equal to, if we simplify this, m n minus mo by mo. This is mo. In the same manner, divided by, if you take LCM here, by m 1 minus m. So this is nothing but mn minus mo by mo into m by 1 minus m. Keep the point in mind. Mn and mo are normal molecular mass and observed molecular mass, whereas this m represents number of particles undergoing association. So this is alpha. Now let us have a look into the relation between association, dissociation and Van Hoff factor. If there is no association or dissociation, if there is no association or dissociation, I equal to 1. If there is association, I is less than 1. If there is dissociation, I is greater than 1.